Good evening, everyone, and thank you for finding the correct lecture theatre. It's very nice to welcome Nikolay Shahpazov to the university. I saw him talk in the summer. I went with Scott. We went to this is what I do in my spare time. Went to a brickworks in Buckinghamshire, but saw Nikolay talk about this great project he's doing, where using waste material, earth, subsoil dug up from site and turned into construction material, obviating the need for landfill tax and all sorts of other things. And that was the kind of start of it. But you suddenly thought, well, this is an obviously brilliant idea. And it was a really great talk, very inspiring. So I hope you'll enjoy that this evening, and thank you, Nikolay, for coming. Just a quick note to say, next week, the Thursday evening talk is not on Thursday, it's on Tuesday. So I will send a note about that tomorrow. But and it's Jan Balbalago and another colleague talking about bamboo construction, and she's a really great speaker, so please come to that. But anyway, thanks, Nikolay. Thank you very much.
Cheers. Thank you.
So shut that door. Yeah.
Okay. Hello, everyone. Regenerative building and why the world is running out of time and sand. Yeah. So probably the more kind of unexpected is the sand here for many of you, and I believe me, is also for the construction industry. It's like there is for an issue that is so big, it's really bizarre that not many people are aware of, and it's it turns out to be a fundamental issue. So going back to resource, the amount of raw materials used by human beings has more than tripled since 1970s. We're cutting trees down faster than new are growing and mature, and basically it's that cycle of consumption that actually outpaces what the available resource is, and obviously in addition to other stuff like carbon, release of carbon, etc., etc. We're now experiencing unprecedented levels of exploitation in the history of life on Earth. Such high levels of resource depletion cannot be sustained, mitigated, or their negative impact balanced out without radical change. So that's the difficult bit here. I mean, especially even if we just focus for the construction industry. What is that kind of radical change? Being sustainable, is it a radical change? Yeah, I don't think so, because if it was a radical change, we would have been there by now. So yeah, I mean, how many years do we need? If we carry on like this, you probably have seen stuff like that. It's just, yeah, it's nuts. So, but where do we start as architects, as designers? It's overwhelming. There's so much stuff, so many materials, so many products out there, so many claims. How can you do the right thing? So I would suggest that the most important thing is to start from one of the most common building materials that we've got on Earth, and that's actually what's beneath the topsoil. So beneath the organic soil, you've got gravel, you've got silt, you've got clay, you've got sand. And in a way, this is one of the kind of, as you like, the backbone of what we should be building with. And it's critical because it's a local resource. So our task is now to find, and very quickly, various ways to produce various building products out of those, out of that mass, but obviously in a way that that mass can perpetually be reused. So you don't make a product that then has to go to a landfill, but actually you keep the material in its raw state. So this is a map of like the different soil types across the world. And sorry, is this one? No. And then, yeah, you can see basically the process of from the kind of immature soil where it's like bedrock and rock, and obviously through the various like rain and various other processes, then breaking down of the rock, and then forming of all these different layers. And it's like a very complicated geological process of, yeah, like chemical, mechanical, and yeah, all sorts. But basically, this is the base, and we are kind of working in that area there, where basically you find your gravel, sand, silt, and clays. so beneath the organic. And this is a kind of interesting diagram. It's like a section through the world, if you like, or kind of equator and the pole here. And you can see, obviously, with the precipitation in the kind of equator, the kind of the breakdown of the bedrock and all the various levels of soil is so much greater than, for example, the pole or whatever, the temperate climates and or the desert, and kind of how it varies. So just to kind of give you an idea. So what have we got? We've got sand, which is the kind of, that's the size of the sand, there's the size of the seal, and there's the size of the clay. So the clay is very, very small, but it's fundamental. So that's your kind of cement, if you like, basically. This is how you make your clean concrete. It's the clay is your binding agent, and it's very important. We'll probably touch on it later on, but it basically, they're very different. There are different types of clays, and then clays have been created in. There's like three different ways that clays are created. But yeah, and it's also like what you have to think about the clays is that basically they are flat plates rather than kind of tiny grains. And then beneath the plates, there is always a thin layer of water. And actually, that's quite important. So there's always a kind of active element in the clay. And then as they obviously then interact with other particles, then they start to kind of interlock. So in earth construction, so this is a diagram of the big round discs are sand, and obviously these are your clays, and the bigger parts are silt, and then there's like silt also varies in size. But the basic principle for earth construction, whether it's round earth wall or earth bricks, etc., is that compacting of the void. So if you've got like a pile of earth, it's got 50% voids in it, as it's kind of dug out and just stacked in a pile. And when we compress it, let's say in rammed earth, when we're ramming it, we go down to 30% voids. But this is how we get the strength in the blocks. So moving on to sand, and I would recommend this book to absolutely everyone. This is what you need to read next week or this week or tonight. Basically, it's so important. I wish I was given this book when I was my first year, or it wasn't written back then, but yeah, the title is probably a little bit misleading. I read articles about it, and then I came to kind of purchase it and read it. It doesn't feel that the title communicates actually what it really conveys. But yeah, so if you now Google "world is running out of sand," you find out lots of articles. I think especially around 2018, there were lots of articles about it. But as usual, kind of. A lot of them are inconclusive, and yeah, it's like, oh, why it's the issue, etc. But going back to the book, and that's the first chapter, kind of first sentence. It's about sand is the most important solid substance on Earth. The literal foundation of modern civilization. And then he goes on to basically, it's whether it's abrasive products, whether it's like ceramics, whether it's chips, whether it's glass, concrete, you name it. Basically, everything that we kind of touched on, or it's kind of come into contact with sand, or it's got some kind of sand content in it. And then, yeah, so why are we running out of sand? Global use of sand is set to soar, and you can see here in kind of billions of tons, close to 30, and then it goes even further. You can see actually against other kind of commodities where we stand. It's absolutely insane. And it goes down to lifestyle. If you think of like 1900s, the majority of the world, how people were living and what they were using, and so it was this kind of contact with nature, and and obviously we weren't surrounded by stuff and concrete and buildings everywhere, and so they didn't have that issue. But now humans are estimated to use nearly 50 billion tons of sand and gravel every year. This is enough to blanket the entire state of California. And obviously the purple here is the state of California. So you can imagine what we use every year of sand. So that's the equivalent of spanning the world in a 27 meters by 27 meters wall, dense wall of concrete every year. Can I imagine how much concrete we pump out? Average time cycle of sand around 200 million years. Mostly quartz is formed by erosion. So again, you can see the kind of the journey of sand, the way it starts from the mountain, and then how it then trickles down the valley, and then gradually forms into a small particle, the quartz. So it kind of falls off a larger rock, and then that's disposed in the kind of valley of a river. So it's 200 million years of cycle, and we are just taking it and then using it in a kind of one-off kind of way, putting it in concrete, glue it in there, and it's lost forever. And then again, more kind of different types of quartz and different, it's quartz and silica, different types of sands, which we use for different purposes. And then going back to concrete, I mean, the real issue that we've got about the kind of the insane volumes of CO2 that we emit every year. And some examples of sand and extraction. But the sea one is actually what is now very, very common in the UK, and not only in the UK. Though the supply may seem endless, usable sand is finite resource like any other. Desert sand does not work for construction. It is too round to bind well together. So yeah, this is the current way that a lot of our sand in the UK comes from, just dredging kind of the seabed with this huge hoover, which has huge environmental impacts. And yeah, you can imagine the embodied carbon also on kind of running that operation is significant. At the turn of the last century, modern concrete was thought to be as permanent as stone it mimicked. None of that turned out to be true. And it's down to the chemistry of the concrete. And there is a kind of the inherited weakness, which is bound to its chemical formulation, but also the fact that you've got reinforcement inside. So when we compare the kind of some classical concrete incredible structures with modern structures, we don't really talk about the same material. They're basically the kind of the chemical makeup and the way it kind of weathers is very, very different. And then, yeah, I mean, that proves it. The Roman engineers found out that adding horsehair helped with concrete shrinkage, and putting a bit of blood or animal fat in the mixture withstood the effects of freezing water. I mean, yeah. You wouldn't give this specification to your structural engineer. Modern concrete fails and fractures in dozens of ways. Heat, cold, chemicals, salt, moisture, all attacks that seemingly solid artificial stone, working to weaken it and shatter it from within. So yeah, you probably have seen this kind of weathering of concrete on like bridges and underpasses and buildings, etc. And that's kind of also, I think, referred to as a kind of concrete cancer, where because moisture gets to the reinforcement and then it starts to kind of rust and expand and contract, it kind of just basically shatters it. The disease that will kill your reinforced concrete depends on where you live, and then various examples of cold climate. And actually, these are extracts from the book. So yeah, when you buy the book and read it, you read it yourself. Can sand be recycled after it has been used in concrete? Yes, but actually you come up with a very kind of low quality aggregate, which is not really suitable for most things. So, and it's very expensive. So this is the project which I'm currently working on at the office. So, I mean, as I'll give you this lecture about not using concrete, I mean, this is what I'm currently building near King's Cross. As you can see, the foundations are almost as high as the building, and they're all concrete. So yeah, not very happy about it, but we'll come back to this one, yeah? So just, I want to move back a few years, 2017, I used to live in Devon, and I moved there with my family, trying to do the right thing, be green and all that, had an electric car. So yeah, I went there and I wanted to do eco self-build. So I started a project I wanted to do as green as possible, kind of affordable building or house to build. So I looked into what's available there. You've got obviously timber, turf, water, straw, subsoil. And then inevitably I looked in Cobb because Cobb is also local to the area. And then, then I started that's how I kind of familiarized myself with earth. So you find your subsoil about 1 meter beneath the topsoil and then mix it with straw and water. And then these are basically then you go into what basically different proportions of how much straw you need to how much subsoil and how much water. And then, basically then kind of get into the technical. But that's kind of quite important because when you move away from kind of the conventional ways of building, you really need to become an expert, even if you're not an expert. Then you need to know more than the experts in order to avoid any risks associated with unknowns. So I looked at Cobb construction. So this is a section through a wall, which is about 0.55 U value. You can't pass building regs with that. So we need to find a different way of building the houses. We couldn't just mimic what was traditionally done there. So with the structural engineer, we came up with 450 Cobb wall, straw bale insulation on the outside, and kind of timber cladding. And then this would give us 0.11 U value, which is kind of beats what building control wants. Then looked at the roof, the thatch roof there. The locally kind of thatch roofs now are too expensive. Actually, it's a fortune. You need to spend every 5 to 10 years. You need to spend 20 grand or something or more to replace it. And we just said no. And we looked into then turf roofs because again, you can get the turf from the site. And and then it lasts 30 years. Then some basic principles, obviously to keep the Cobb wall dry, to have a plinth, stone plinth, not to get wet, big overhang, which helps also with kind of rain and also some kind of give you a bit of cover from the sun in summer as a kind of a basic principle for the house. Then looked at the kind of what we typically have like a resource use and waste in buildings in terms of like electricity and water and basically, just kind of creating, in a way, kind of pollution. So we looked at closing that loop and compost toilet, reed bed outside, and so kind of all those things, obviously, to minimize as much as possible what goes out as a waste, and then actually either turn it back into a resource or minimize its use. This was the plan for the site, 5 houses. So we kind of, each family was to have a small plot around the house. The rest is for oak orchard. We've got orchard, we've got oak plantation, wild meadow, and then, so basically it's all about boosting the biodiversity, replanting pretty much the carbon that you've emitted. So you kind of, over the, 30 years, it kind of reabsorbs it by what you've replanted. And in a way, again, you kind of balance things out. And not only that, but we had an ecologist here on that job, and she did a scheme so that by doing that on that site, you improve the biodiversity on the site if you compare it to just being a kind of a grass field. So in a way, because of the ponds, because of all the things that kind of are done and planted. So in a way, that's a kind of a benefit as well. And then, there was like all sorts of things like, no concrete, no structural steel, no petroleum-based materials, and all this kind of, lots of the big volumes of mass comes from site or nearby. No toilets, all toilets will be waterless, and so kind of lots of this kind of stuff. But we went to pre-up. Then the planners kind of stabbed us in the back, and then the parish council also stabbed us in the back, and then it was when we decided to come back to London. That was the kind of a diagram of what the house would look like. is earth construction scalable? So I'll show you, that's another competition I did a few years ago for a university building in Sofia. With the engineer, we looked at the soil beneath excavation, and it was good for rammed earth, so we wanted to do rammed earth walls, which are then attached to superstructure, which is timber, glue-lam timber internally. And then we had like proposed reed bed insulation and earth screeds as well beneath the floor tiles everywhere. So again, minimize use of cement-based materials. That was interesting, actually. That competition, we came fourth, but then the first three should have been disqualified. But then it was Bulgaria, so it didn't matter. So we didn't win. I'll show you another competition, which I did with Atelier 10 and Expedition Engineering. So this is for an art gallery in Finland. But here I would like to kind of focus more on the fact that the way you design for regenerative buildings has got to change. So you can't just use the same design methodology as you would use with modern buildings or kind of mostly kind of business as usual approach. It's different, and you almost like you need to first design the material system for your building, and then to start to kind of shaping things out, and then to think of like what can go where. So it's kind of very different than come up with some idea, some shape, and then try to kind of plug things in. So yeah, that's the site. So we looked at the site. So kind of temporary is located on Esker, which is between two lakes. And then the soil, so Esker is where glacial water carries sand and gravel. And then we located we then tested from the available information. We had to look at the sand and the gravel there. It was good for earth construction. So we wanted to do, basically, that's Martin Rauch. If you don't know him, look him up. He does amazing. He's got this mechanized way of making round earth panels. So we proposed the same methodology and the same kind of use of material. So you make about, I think they're 450 thick round panels that are lifted into place. And then you close the gaps with earth, kind of mortar, and then they kind of mostly disappear. Then for the superstructure and for the floors, we looked at ribbed panels, which are better than than the CLTs because they're more efficient. And then we saw what spans. I think they're about 7.5 meter spans. And then also for the foundations, kind of round rock, which is that kind of vibro system, rather than concrete. And then for the insulation, we proposed these structural panels, which are hemp and resin, which actually they're no more available. Post-Grenfell, they're no more available on the market because the testing regulations for fire are now so kind of insane that even kind of sensible products cannot make it. Just because it's got resin, it's a too kind of, I think, component material, then they can't afford to do the tests every few years. So, but anyway, so back then that was what we proposed. The insulation was very good levels. It's carbon-wise, it's also very, very kind of, I mean, zero carbon. Yeah, so that's the kind of the diagram of like, again, I was saying like a resource-based design. So you kind of design your material system before the building. You find your ingredients, your components. And then it was the whole idea that kind of they're either biodegradable or the resource is retained within the material for further reuse. For initial sketches, as I said, kind of really without even thinking of program, just to see what you can do with that material system in a kind of a reasonable way, kind of in terms of plan, and then the kind of sections and the spans, etc. Then Atelier 10 proposed thermal labyrinths beneath the ground to cool and heat the air in summer and winter in order to minimize energy use. And then also we looked at making soffit panels out of earth as well, which again, they help with internal humidity and also kind of less carbon. So that's that's a plan view. You've got your RAM panel. You've got the hemp panels, which are sandwiched between timber. That's the section, and this is how the floor connects with the ring beam, and this is a cross section through the floor with the soffit panels. So that's the kind of all your components for the wall and the floor. And then generally volume of the building. That's that with the context of other buildings. Then that was kind of external view and internal spaces. So you see the that kind of ribbed effect of the soffit. And then so this is Atelier 10 diagrams. Again, like really they did really well. It was all the kind of air comes via those labyrinths at the beneath the slab. It's distributed internally, and then it's captured, and then it's recirculated again. The heat is recirculated. So and then so that's that, and then so that's their kind of summary of their scheme. But it performed really well, very low energy demand, etc., etc. So this was their carbon analysis. You can see basically here from the 417 kilogram of CO2 per square meter, the percentages of where the carbon is, so 3% for the PVs, 22% COT, 15% building services. So you kind of see, 4% local rammed earth facade. That's what we were just saying, is that it's so important to bring earth products within your building. 4% rock piles. Usually, the majority of your carbon is in the superstructure and the foundations. This is again the summary of the carbon. But the shocking thing here was that after all that, we came about B. So this is a chart of A++. So we should be kind of zero carbon. Now building should be here. After all this, you still come just about A, but kind of between A and B. So you can imagine business as usual buildings, even with their claims, where they venture in that, and how much further everything needs to be pushed in order to get there. So that's very important to keep in mind, that even if you do everything, and this is really pushing it, that competition entry was really pushing it within the kind of reasonable limits. But it's a hell of a task. This is the winner of the competition. And you can really see basically I kind of just imagine concrete bunkers. It's like there's not many materials you can make this of, and the whole aesthetics was really based on this kind of concrete, which is a real shame. I think that our competition entry did really badly, actually. From 500, we were probably 420. I don't know, but never mind. So back to the project I'm currently working on. So what can you do? What can you do in order to kind of get there or start going in the right direction? Going back to the earth and seeing the site investigation, see what type of earth, and what can we do with that, and we can do blocks. So then we can say we've got some concrete blockwork in the basement. We want to replace it with earth blocks made out of subsoil from the site in King's Cross. So it was a long journey. I first had a contact with, chat with Roland Kieber, who is a earth construction specialist. And he said, go to your contractor and just, as they're piling, just ask him to give you a few bags of freshly pulled clay out of the ground, which is really unusual, of course. So I did that, and they were quite amenable. And I said, okay, fine. It was a bit weird, but so he gave me the soil, and I sent it to him. He made a small brick. Then we showed it to the client, and they got excited. But then the first reaction was like, can we sell it? So we said, no, look, it doesn't work like that. It's about building on site, et cetera, et cetera. So we're getting there. So it's kind of moving on, and it looks like it's going to happen. So in the basement, we've got this orange wall, which goes all the way around the perimeter wall. It used to be concrete block work, so now we'll have earth blocks made out of subsoil from the site. So we've already, from the excavated soil, we've sent the amount of soil we need to the block manufacturer, and they are soon going to start producing blocks. So this is what we had before. So we checked U values, and it looks like actually the earth blocks are performing better. This was kind of pictures of the soil being taken away in the trucks to go to the block maker, and then sample blocks being made. And then, yeah, starting to go back, 30-mile journey, and then making it to blocks, going to the building, and then perhaps one day, yeah, they can either turn to ground or be used in another building. The resource is not used. It's in its kind of pure form. So the client ran an article on it. They were kind of quite pleased, even before we actually pressed the button on it. The contractor also did an article on it as well. We made a submission to the Royal Academy Summer Show, and we were selected, so we made a display with the kind of the maps and everything else. But it was really strange that kind of when the articles came about the Royal Academy, there was no mention, and as you can see in this photo, in that article, we are right behind that. So it was really kind of, really, really stuck in the corner. And personally, what was really disappointing is that Sterling Prize winner of this year was, I think, the curator of it. And this was probably the greenest proposition for the Royal Academy in terms of like building in London, building And we were not only shoved in the corner, but also there was like in the publicity and the kind of in the architectural kind of journals, there was no mention of it. So yeah, anyway, hopefully we'll get there. But yeah, it's a long journey. And yeah, this is basically disc made out of elephant dung with lime. Again, it's kind of, how many elephants do you need in the UK to build with? And it just kind of, it's completely insane. The problem is that the whole thing about environmental kind of design is being dragged into this kind of ridiculous conversation about things which are really, out of the question. And in a way, they divert from things that are really credible and simple, unfortunately. So yeah, going back to the earth block. So I had a really, really difficult task to find a way to calculate the embodied carbon of it against concrete block work. The reason for that is that concrete block work is part of a very big industry, and also the cement industry, which also is part of that. There's so many ways to kind of double account or hide figures, and they come up with a figure which, when you compare it with something tangible, i.e. dig the soil from here, drive it 30 miles, so you know how much carbon you use, make it into blocks, so we know how much carbon they use to make the blocks, and bring the blocks back. And we're coming with a figure that is just a third better than what the concrete is, where the sand comes from the sea, the cement comes from all over, some of it, the components from sea, quarries, etc. The cement also emits a huge amount of CO2, etc., etc. So yeah, after crazy amount of calculations and conversations with various engineers and specialists, kind of insane comparisons and all that. So we came up with a figure which now is far, far closer. This is just a map of where all the ingredients will come for the cement, you can imagine, and for the block. So we're talking about a journey which is 30 miles to basically a journey could be hundreds of miles, and they're just saying it's a third. But yeah, we are now, so this is again the kind of showing the cycle, the different comparisons between the blocks and how much basically tonnage of material we will have on site and et cetera. But the important figure is that, it's 1,854 kilogram of CO2 against the concrete, which is 11,620. So finally, we came to a figure which is much more realistic. Again, you had to kind of go through so many documents and have really kind of difficult conversation with so many people. And then, yeah, it's about probably between 8 and a tenth of the CO2 of concrete blockwork. So you can imagine, so that's more radical, that's more likely. Like if we need to reduce the emissions that we're creating from the materials we are producing, this is like, if everything comes down to a tenth of it, we're kind of getting somewhere. So, yeah, the best way to understand the difference between business as usual and regenerative architecture is by reducing the process of designing and building to its core fundamental materials, i.e. ingredients, which are used in both cases. I think this is really important. So you have to, I guess in your designs and in your work, you need to question everything that you put in your scheme. Like, where does this come from? What kind of emissions does this create? What kind of impact this has on nature, on the environment, et cetera, et cetera. And then choosing your ingredients, then to start building up your project or designs, et cetera, et cetera. But then without doing that, without interrogating each one of your main material blocks, you can't get anywhere. Yeah, it's, we know where we'll be heading if that happens. Only when the core ingredients are clearly identified and then environmental impact is understood, we can be certain if the design methodology we use when designing building is suitable to address climate crisis. So that's again what I said just now is that's the most important thing. And this is why, for example, on the King's Cross project, it looks simple. Oh, it's just a block. Oh, it's just, you've got the foundations, but that's important because that's one of your ingredients. You need maybe 20 or 30, but that's one of them. So you can get there. You can get one, and then afterwards you can move to foundations. We've got now solutions for foundations as well. And we can persuade clients, and we can make testing, and move to cladding. So that's very important not to kind of miss the opportunity to focus on the key elements. Both the cooking and the building ingredients are part of a production system which leaves its traces on the habitable environment. And again, I really think that the comparison between cooking and designing a building is very relevant in this case. If you want to eat well, and if you care about the environment, and if you want to understand where that food comes from and what impact has on whether it's a community or the environment, then you can carefully select your ingredients. And then what then you have to do though, is you need to start changing the recipes that you've been using, because if you still want a burger, you may not have some of those ingredients in a kind of maybe in the kind of environmentally kind of credible and decent level of impact. So maybe then it's something that is like a burger, or with other things. And so that's where also the kind of process of cooking starts to change and the recipes start to change because your ingredients start to change. So you can't just go to your grandmother's cookbook and say, oh, okay, I'll do that. Because the key green ingredients that we have now, maybe that come in your veggie box, or maybe that you can have in a local farm, are different. So you need to actually start then tailoring your kind of weights and appetite, etc., to actually different set of ingredients. And then that's the same with buildings. Like we can't just draw shapes assuming that that's concrete and steel, or it's big cantilever, that's fine. We'll do it. No. Actually, if you don't have material system that can produce this big span, and obviously material system that is credible and doesn't have this horrendous kind of an environmental impact, then actually, yeah, sure, go for it. But then you need to go through that process. Cooking requires ingredients. They need to come from somewhere. Their production requires energy, produces waste, and inevitably impacts on the environment. The construction of buildings requires building materials, which can also be defined as ingredients. They need to come from somewhere. Their production requires energy, produces waste, and inevitably impacts on the environment. The core ingredients which are mostly commonly used in construction today are concrete, steel, timber, stone, sand, and various petrochemical derived products. Most of them are obtained through mining and have high embodied carbon. They follow a linear process from the extraction, use, and disposal. So that's basically it. It's once that product reaches end of the life of the building, there's no resource, there's very little value in it, and most of them go in landfill. And in a way, so that's why going to ingredients, you've got to question that kind of afterlife of the material, that other journey. You can't just be specifying materials that cannot be reused, because, for example, this is not only a broken tile, so you say, oh, but the tile can be reused. Well, to a degree, I mean, there is, of course, but they, after a while, start to kind of, they wear off, they start kind of chip, etc. This is also clay and sand and sealed, lost forever, yeah? Because it's been baked, which also has emitted emissions. So again, can you create a roofing material that doesn't need to be baked and et cetera, that it's not gonna waste, it's not gonna lose resource, valuable resource. So again, that's also very, very important to take into account. The core ingredients of regenerative architecture are plant fibers, timber, clay, silt, sand, and rocks. They're obtained by growing them or mining them. Unlike modern buildings, they create the created resource is used in its raw form and is retained within the building as resource for future reuse. And I think that's, again, think of your building as storing resource for future reuse and storing it in a way that can be reused. And I think that's that's very important, and it's very different. And I know that nowadays, of course, the practice of sometimes reusing things from existing buildings that are about to be demolished is getting more popular. Again, not as much, but it's not the same. It's not the same as a lost resource that's been placed in a building that actually then can be only reused as that product. So for example, as I was giving the example with the earth, maybe clay boards or earth blocks, this can be pretty much just chucked back in a pile of earth, mixed with water, and then made into another block, again, without the necessary furnaces and et cetera, or cement, et cetera. So yeah, and this is basically the end of the journey of your kind of earth-based materials. They can also gently go back to ground without any kind of detrimental impact on the environment, and of course with a fraction of the CO2 that other materials would have created. So yeah, that's it. I'm not sure whether I rushed through it a bit too quickly, but I think it's probably good if we can to open the discussion, maybe go back to some slides if people want, maybe revisit some other things, and just kind of broaden a bit the discussion. Yeah, thank you very much.
Thank you. We take some questions, yeah. I'm going to pass the microphone around, if that's all right.
In terms of using natural bricks out of earth and not firing them, how do you then measure the longevity of those bricks in terms of rain and floods? How do you make sure that you have a long enough lifespan for the people who are using the building without it actually being compromised?
Yeah, no, it's a good question. I mean, you wouldn't, so for example, with those blocks, you wouldn't use them externally because, for example, with rammed earth, you go with much bigger, much thicker wall, about 450, and then there is something which is called calculated erosion. So with rammed earth, as the rain starts to hit the wall, it takes some of the finer particles first over the first few years, but then as it exposes some of the larger particles within the wall, the clay behind it, as it gets wet, it expands and actually prevents from water going any further. So that's why you see a lot of the kind of older rammed earth buildings, they've got kind of more textured kind of facade, but that doesn't mean that, it's in any way damaged. It just means that there's kind of, that's what it's Martin Rauch's actually definition, kind of calculated erosion. So yeah, it's, of course, you have to make sure that your products are fit for purpose for where you use them. I mean, you can't just, start putting unbaked kind of roof tiles and expect to kind of, of course. So then you have to go to maybe other materials, etc.
Okay, thank you.
So in terms of the structure using the more environmental bricks, the other half of the building would be using cement or mortar for pointing and such. Is there a...
No.
No?
You can use clay mortar. So the same mix that you make the block, actually this is what we're doing in King's Cross, we're using for the mortar. And actually in the summer, I was visiting a kind of a small village in the mountains, and there it was in Bulgaria, and very large walls. So these old houses, about probably 10 meters high at least wall, with a kind of a smaller round stones. Actually, they were kind of square shaped, but smaller stones. And they all had clay mortar. And this is like in a seismically active area. The building is probably 200 years old. It rains, it snows, and it's high in the mountain. And you go to a structural engineer now and say, hey, let's use this clay mortar for this big wall. They'll freak out. They wouldn't do it. Yeah? And we're in this kind of ridiculous situation where there's so much knowledge being pushed into regulations, et cetera, but then when it comes to this kind of simple exercises which a structural engineer could do, they paralyze. They can't think. So I mean, very few can, but yeah. So you don't need the cement.
Thank you.
Thank you first for the insightful lecture. I wanted to ask, how do you envision taking regenerative architecture even further? Because I think that's something that I know it's not done at the moment at the level it should be done, but what you're saying is actually what we really have to be doing. Like, it's not even questionable, it's kind of compulsory at this point. So how do you see even taking that a step further and even kind of helping the environment around to be?
Yeah, it's a hard one. I mean, as simple as it is, just getting this block approved by the client and the contractor has almost broken me both physically and mentally. And we were at the point a few days ago when it was kind of, it will happen or it won't happen. And it's extremely difficult. It's very hard because probably actually convincing clients and contractors sometimes is easier than convincing your own boss. Yeah, I think that there is that thing that we are fighting with. There is awareness, which is far bigger than it's ever been, but then it's so easy just to kind of go down on kind of business as usual, but dressed up kind of under a bit of sustainability route, you know, and Yeah, we had actually one of our early kind of stages, feasibility stages, was for a very large scheme just by the Thames, and there were lots of buildings to be demolished. And then we had early conversations with the engineers, again, probably one of the most known kind of outfits. And we said, oh, concrete-free foundations, can we do concrete foundations? He was like, absolutely no way. The clay, no. He learned this really big email. This is like really experienced engineer. And yeah, I spent like, I don't know, a month probably kind of digging through like archive photographs of old foundations and stuff and putting together various things, and then approached one of the structural engineers who was my tutor, who is really, really good. And I said, like, look, am I crazy, or what do you think? And he was like, oh, no, actually, it makes sense, and you can do also this. And all of a sudden, you come with a solution. So I made presentation at the office. And I said, oh, by the way, Oh, okay. So we did a bid recently, and then one of the bosses came to me and said, oh, can you give me your research so we can try it in the bid? We tried it, and it's gone in as this kind of concrete-free foundation. So whether it will happen or not, we don't know, but we won the bid. Now it's kind of, the scheme is happening. But again, what my boss doesn't realize is actually what it takes from grabbing an idea to actually materializing it. And the kind of the pitfalls and the kind of the kind of brick walls that you're going to hit between trying to do it and actually doing it, it's a hell of a task. And I think, but of course, we've got to try to do it, but it's very, very hard. And yeah, I really think that kind of architects, especially that kind of my generation and maybe those kind of a bit older, like 10 and 20 years older than me, they need to really be almost like re-educated in actually what really needs to happen. Because it's so easy to just get lost, oh, cement substitutes and oh yeah, cement is actually not that bad, and yeah.
Okay, very sad. And another quick one, where was the, which university was the building for Bulgaria?
I was for the medical university. It's like one of the most prestigious universities in the country. Yeah.
I know. Yeah. Okay. Thanks.
Hi, Nikolay. Thank you very much for a very insightful lecture. In fact, really relevant to my own dissertation topic. So, yeah, it was wonderful. I wanted to ask, how would you classify? Maybe a very similar question, but how would you classify the barriers for scaling up? Regenerative architecture in the UK? Would you say that you mentioned about the culture in the industry, but would you talk about legislation in terms of barriers?
Yeah, that is an issue. But again, if you've got a good client, if you've got really good engineers, I think perhaps actually here I should mention, going back to designing your material system, I also think that in terms of practicing, now we need to move away from you make a design, you do a pack of details, it goes out to tender, and then obviously they find a contractor. So some of those things need to be locked much more earlier with the supply in mind. If in the next job we want to do earth blocks, we're not going to go to say, oh, just go on open tender and just see who can make earth blocks. No, we say, oh, H.G. Matthews are doing the earth blocks. They're the only ones who are doing it now, and actually they can deliver on that. And so it's almost like you lock a supplier with the design early on, and it's a done deal. And the same is if it's Steve Webb's stone. You go to a stone masonry company and say, oh no, Pierre is the guy, he's the only one who's doing it. You lock that, and that's that. So the way you design and procure needs to change as well. And then, of course, there's the kind of risk, there's testing. So I think that's also the thing, that testing is expensive. Takes time. It's got risk. And then obviously everybody wants take your risk and everybody freaks out, no? So it's a kind of course, it needs to be managed risk, but yeah, it changes the dynamic of how projects are shaped. And my personal opinion is that even in early stages, feasibility studies, let's say, or maybe pre-planning stages, I think that this stuff needs to come much earlier. Rather than you make designs and say, oh, later we think what kind of materials, we choose something. No, actually, you almost need to, the planning needs to be much bigger chunk of design work, because we really need to find the key ingredients, so that you really have something credible that gets approved, and then, of course, then you go through testing. So yeah, I think that the way you design and procure has to change in order to adapt to that.
Just one quick one. Could we reference you on the embodied carbon for the earth bricks?
Yeah,
And
sure.
where can we
Just
find
say, what's it? Work in progress. Work in progress numbers.
Thank you.
Yeah. No, it's fine.
Yeah, I wanted to appreciate you going into the detail a bit more about how difficult it is to have those conversations with client, with your own team, etc. Because lots of times you see the result and you don't see what it really is like, and people don't get to appreciate, because that's where the change is. It's very difficult, arduous, etc. I mean, I work as a construction manager full-time, so I know what it can be like, and the attitudes and so forth. And so I want to ask, it seems like you've done a lot of this legwork yourself in your own time. Is that the case?
Mm-hmm.
Or did your practice give you extra time or a team to do this? Because it's a lot.
Yeah, so it's at Bennett we've got a sustainability team, and so I'm part of the sustainability team, and I'm looking up after the kind of regenerative materials within the company. But most of this I've done outside the company. I mean, all these competitions and stuff I've done on my own spare time. Mm-hmm. Even the last one in Finland, I did it in lockdown. I just took 3 weeks off work, and then I just did it in there. So yeah, nobody will give you the time.
No. But your practice is, it seems like that's something that's a key principle of theirs that they actually do. And is that something lots? I don't think there's going to be many that are like that.
I think we talk a lot about it in the practice, but I wouldn't say, it's a tough one. Yeah, as I said, the awareness is there, but when it comes to actually really kind of shaping designs, even early on, we're not there yet in terms of kind of the key principles, because the problem is that if you don't lock some of those things early on in your new designs, then it's too late. Yeah? So that hasn't happened in the practice yet. Are there many other? There are, but I mean, yeah, it's yeah.
Okay, thank you.
It's not as common as it ought to be. Yeah.
Okay. Well,
Thank you.
thanks.
Hi. Yeah, I also wanted to ask, because you mentioned for BREEAM scoring, what do you think are the biggest limitations in the scoring system? And I don't know, what do you think has to be changed, or do you think it's working well for where we should be in terms of regenerative architecture?
BREEAM, you mean?
Yeah.
Do you mean the embodied carbon kind of calculation?
I mean,
this is what you mean?
I mean, in terms of
BREEAM
like
is
as a
not
scoring
going to
system
give
in
us.
general, right?
Yeah, I mean, yeah. I think, yeah, BREEAM is, in my mind, is a bit of a joke. It's more. I mean, yeah, you can really hide there behind kind of numbers and still not do enough. I think that the real task is when it comes to kind of crunching the numbers of the embodied carbon and then the operational carbon, and how you do that. And as you saw on that diagram, is that, I mean, even that kind of finished project is you have to go so far, and even then you're not A plus or A plus plus. I mean, what do you have to do to be A plus or A plus plus? I mean, it becomes insane. So yeah, I think that it's going back to, I know that sometimes it may be overwhelming, and that's why you have to start somewhere. And this is where I hope that kind of example of the block is quite good, because you can start from one unit, and then you can then kind of, and that was actually my hope, is that if this goes through and goes ahead, then you can think, okay, so can we do also Earthcrete, maybe in the next job? Can we do also? And then start to kind of bring more and more ingredients and make everything far more kind of palatable and incredible and diverse. But you shouldn't get paralyzed by, like, maybe perhaps of kind of lack of, I mean, yeah, if you look at sterling price, I mean, is this regenerative? I mean, it's a joke. It's a joke. So you have to, I mean, actually, you really need to start from scratch. And yeah, unfortunately, kind of the industry is not there yet. And the awareness of how radical the change needs to be is not there yet, I think.
Thank you.
There's one more in the back there.
I'll get you the microphone.
Thank you for your talk. It's very interesting. I'm not sure if what I'm saying I'm not sure if I can formulate this as a question. It's more of an observation. But what you're talking about reminds me of some things that Mies van der Rohe said back in the 1920s in Berlin, when there were all sorts of conversations about changing the building industry. And I think the sort of essence of the question proposed to Mies was, do you think that design can change the building industry? And his answer was no. The only way the building industry will change when there's a new material. And I find what's interesting, I think you're saying that in your talk. And then I was sort of struck with the Royal Academy comparison of the elephant dung sculpture, and then your sort of modest piece set within the sort of framework. And then you referred to it. I think was it a Herzog and de Meuron building, the Ricola building? Is that by the Herzog and de Meuron?
Which building? Sorry.
The Ricola.
The Ricola. Yeah. It is Herzog and de Meuron. Yeah.
So is that art that? Because I think that can design change the building industry? No. I think Mies is right about that. It can't. Only a new material can do that, which is what you're saying, I think. Seeing the schism in the Royal Academy between your attempt to sort of tell the truth and then the rhetoric of the elephant dung sculpture. But I don't think we should devalue that, because it probably the elephant dung sculpture conveyed a message, perhaps in a more not in terms of truth, but in a sort of rhetorical way that perhaps your piece couldn't do. And then I'm thinking that Herzog and de Meuron, given the way they set up their practice, as Herzog's the art, he can cope with the self-presentation side, and then de Meuron's, as I understand it, is more interested in systems, which I think is a lot of what you're talking about. And then the way they sort of managed to play that together to get something out of most of the projects that they've done. And none of this is a question, but in a way it is, because I'm asking you what well, it isn't a question, but answer it anyway.
No, yeah, it's a very good observation. I think it's spot on. I wasn't aware of that quote by Mies, but I think it's very, very relevant. And yeah, as you said, material can change the industry, and that's what needs to happen. And almost like that's why I think that's why we need to go to the specialists who understand the material, and then together with them, we need to come up with ways to implement those materials and create systems for them that then can be scaled up, et cetera, et cetera. and almost like this kind of function, design, look, it becomes something that is kind of less relevant. It's almost like, oh, it will come within the process, and kind of less focus on it, less kind of anxiety of like, how is my building going to look like, and where is the bathroom kind of thing. But yeah, it almost kind of catches up. I still feel that, I mean, the Royal Academy creation was a big disappointment. The problem is when you read that article about the elephant dung, it so kind of misses the point, And actually, I mean, I wish it was doing what you were saying, but it kind of says that, oh yeah, well, you can do something out of this, and it's kind of green, but actually it's not even really green because you add lime to it anyway. So it kind of, you stabilize it, and then afterwards, I mean, yeah, it's really kind of, so it's a shame that because the conversation needs to be brought down to the very simple elements of that kind of argument, and I think that's what the elephant dung is not doing it, and it needs to start from simple and build up into kind of complex.
Thanks, Nikolay, for your talk. And for these young architects here, they really get a sense of the struggle and, in a way, the conflict. You started that housing project in Dartmoor, and now you're working for a big practice in London, working on buildings like that. But you are, you're crunching the numbers and you're struggling against the system. So I just wanted to, I don't know if this is a question either. I'm just wondering about the word joy, and I don't think it's a dirty word as we go forward with our massive challenges. And when we went to H.G. Matthews over the summer, we went to the nursery built out of earth blocks. They said it was oversubscribed. Families wanted to put their children there. During all the heat wave, it was the coolest place to go. And so there is another side to this, which is, the human experience of these materials, and yes, the joy that they can give us, and we mustn't forget that. And as architects, that might be the side of things that we are the most interested in. I don't know if that's a question.
Yeah, no, I agree, and I mean, I wish we could talk about experience as well. I think that it's a whole new kind of thing that is obviously in parallel to that, but we can't even get to it because we're stuck at A, B, C still, of trying to bring those vital ingredients and then to try to build with them, and hopefully at some point, if we've got something that is credible, we can then start to shape the kind of the whole experience conversation as well. And as you said, the kind of the whole joy of like tactile experience and various kind of light conditions and all sorts of things. But unfortunately we can't get there because we are stuck in this kind of situation where almost we're so used to designing almost like a meal without ever tasting it or without ever anybody tasting it. It's a kind of weird word of fixation of, buildings should look in a certain way, but actually nothing is really properly interrogated, The experience of them is not properly interrogated. The tactile connection is not properly interrogated. The environmental credential is not properly interrogated. It's just kind of this imagery, They're kind of tasteless almost like, They just, they may say wow, or they may kind of scream at you now and then fades away, and that's it. But then the amount of waste that you inherit with that is phenomenal, and the amount of resource that you lose. So I'm with you. I mean, I've been kind of on the side doing a lot about research about experience and buildings, etc., human experience, nature. I wish I can also bring that conversation in, but it will get so complex, and it almost like it will kind of discredit that kind of little steps that we first need to do in order then to bring other topics in it.
Look, thank you so much, Nikolay. It was wonderful talk. I love the analogy, the ingredients, the idea of chefs, of cooks, and in a way, it's like we need to train the chefs as well, but we also need to train the cooks and all the rest, and that in a way that this idea of what the construction industry is, as well as the designers, and we're all part of the same thing. And I think it's really, I think this idea of ingredients is really super powerful, and understanding what we're doing and what we're making things out of. And great talk. So thanks so much. Thank you.
Thank you. Oh, I'm glad.